ಇನ್ನು ಕನ್ಸಿಡರೇಷನ್ ತಗೊಳ್ಳೋದಕ್ಕೆ ಬೇಡ.
ಯಾವುದು?
ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ ರೈಸ್ಡ್ ಹ್ಯಾಂಡ್ ಅಂತ ಬರುತ್ತಲ್ವಾ?
ಓಕೆ.
They will just keep on just clicking something like I am here.
Okay.
ಅದು ನೀವು ಯಾವಾಗ ಇದು ಸೆಷನ್ ಅಂದ್ರೆ ಇದು ಮಾಡೋದಕ್ಕೆ ಶುರು ಆಗುತ್ತಾ? ಇನ್ ಕೇಸ್ ನಾನು ಇರ್ತೀನಿ ಇಲ್ಲ ಅಂತ ಅಂದ್ರೆ ಇಲ್ಲಿ ಇರುತ್ತೆ ಮೋರ್.
Ma'am, you may want to go on mute.
Okay.
Shall we start, ma'am? Time is 9 o'clock.
Yes, I'm ready.
Yeah. Good morning, teachers. So we are happy to meet you again for a newer session. So we are privileged to have Dr. Lalitha Rangarajan, who is a renowned professor, an expert in bioinformatics. So who is serving as a professor in the Department of Studies in Computer Science, University of Mysore. She has done her graduation from Madras University and Bharatdasan University. Madam has also done Masters of Science from the world's one of the popular universities in USA, namely Purdue University. And she was able to complete her PhD studies from Mysore University. Madam has been serving in various key positions in teaching profession in the University of Mysore, JSS Polytechnic and SJ College of Engineering, Mysore. And for some time in Purdue University, West Lafayette, Indiana, USA. And now currently associated with the Department of Studies in Computer Science, University of Mysore. Madam has been serving in various key positions as members of high-profile boards of examiners and boards of studies in various premier universities, namely University of Mysore, Calicut University, and few universities abroad, namely Huanghai University, China, and so on. Madam has completed guiding 6 doctoral candidates and currently guiding 5 doctoral candidates. And the research interests of the expert are dimensionality reduction in pattern recognition, bioinformatics, image retrieval, medical image retrieval, code similarity detection, microarray image processing, microarray expression analysis. Madam has published 1 book chapter and more than 30 international journals in peer-reviewed popular journals and many international conferences and so on. So we are really happy to have such a renowned expert amidst us to share her experience. So I request Madam to throw light on the application of mathematics in combinatorics, mathematical induction, sequences, and series. Madam, please.
Thank you very much for your introduction. Good morning, participants. I can speak your local language.
Yes,
occasionally, I will mix Tamil also when I am talking to you all. I'm going to cover. Shall I start on the lectures now? Or?
You can start, please, ma'am.
Okay.
Sasi, excuse me, ma'am. Sasi, I think it is streaming online in YouTube.
Okay. You were asking somebody. Okay.
Yes, sir. Yes, ma'am. Yes, just
nobody is around here.
No. He is online.
Okay.
Sasi, are you there? It is already streamed online.
It's already done, sir.
Okay. Madam, you can please start, ma'am.
Okay. So I'm going to talk today about background, a very little background, of course, and a lot of applications on the topics of combinatorics, induction, binomial theorem, sequences, and series. We'll start the topics one by one in the same order. Okay. The agenda is going to be like this. I'll pick a topic. I'll give some basic definitions and introduction. I mean, in case somebody has forgotten and lost touch, you can have a quick introduction of that. Then go through some basics in brief. If this is not too much, absolute essential only are discussed here. Discuss applications in length. Then the emphasis is more on applications rather than foundations and problems. Okay, combinatorics is the first topic I have chosen. This is a branch of mathematics concerned with counting. So you all must be familiar with combinatorics, at least the words permutations and combination. Counting can be means to obtain results or can be means to obtain results or solution itself. Applications are many and in diverse fields in science, economics, biology. These are only few fields I have named. It's actually applicable in every field. Primarily concerned with finite sets and systems, but can be extended to infinite but countable sets. Okay, infinite uncountable sets doesn't go with combinatorics. You have to have countable sets, but it can be infinite. Okay, there are many more enumerative methods available in mathematics. I'm going to cover only permutation and combination in this lecture. For want of time, we can't be going through only enumerative methods. There are so many topics else to cover. Okay, permutation is different ways of arranging items in a sequential order. All of you must be familiar with permutation, and you know many theorems of permutation by having experience in years of teaching students. You must be more proficient in many theorems than myself. As an example, number of ways of seating arrangements of 3 committee members is 6. So what are the number of ways of arrangement is like this: member 1, 2, 3. Okay, then 1, 3, 2, 2, 1, 3, etc. 6 in number. Okay, the same thing can also be found. This number 6, we need not list out all these arrangements. We can simply use this formula of 3p3, okay, which is same as 3 factorial. Now, suppose C1 and C2 are to be seated next to each other. Okay, then that means this particular combination is ruled out. They are not sitting next to each other here. Okay, then this also is ruled out. Okay, no, not this one, sorry. This one. C1, C3, C2, that also is ruled out. So the remaining number is 4. Then the number of arrangements possible is 4. This can be simply calculated using this number. We need not, again, I insist, you need not list out everything and then find out which are the arrangements where C1 and C2 are not together. Okay, so we can simply use a formula like this. How did I get this formula? Okay, so C1 and C2 are together means, so you consider them as one entity. So there are totally 2 entities. One is C1, C2, and the second one is C3. So I get total number of permutations to be 2p2. Okay, and then why am I multiplying by this 2p2 is because C1 and C2 themselves can be seated in first C1, then C2, then C2, first C1 later. So that makes it 2p2 again. When I multiply these two, I'll get a number 4 again. Okay, the notations are, some people write it like this, some write it like this, npk with these two in the suffix, p of n comma k, p n k, p of p suffix n comma k, so many varieties. I'm going to stick on to this notation because it was easier for me to type it. So I go through this particular notation. But however, when I'm talking, I may show you this formula, this notation, but then I may use this wordings npk. Okay, so p of n comma k is equal to n factorial divided by n minus k factorial. All of you must be familiar with this formula. Now in permutation, order is very, very relevant. Okay, so we'll move on to the definition of combination. Some basics is shown in this slide. Combination is one of the ways of selecting or choosing k items from available n items. Order is quite irrelevant in this. Okay, so let me go back to the previous slide. So for instance, this combination C2, C3, C1. Okay, so this is same as any other C1, C2, C3. So there is no difference between this sequence and this sequence in combination. As an example, consider the problem of selecting 2 people from a group of 4 applicants for a job. Then the number of ways of doing so is we can pick 2 people from a set of 4 applicants in 4 C2 ways. Okay, the choices are A1, A2. When I list out the choices distinctly, it will match with this number of 4C2. 4C2 is actually 6. Okay, so it comes out to be 6 here also. A1, A2, A2, A3. So when I list A2, A3, there is no necessity to list A3, A2. They are both one and the same in combination. Okay, now note that NCN is equal to 1, which you all know, whereas it is n factorial in the case of permutations. When we say NPN, that comes out to be n factorial. Now, as before, the various notations are available. I'm going to stick on to this particular notation, although sometimes I may show you this particular notation and then when I'm saying it, I'll I may probably say it as NCK. Okay, therefore, actual value of NCK is this particular value, n factorial divided by n minus k factorial into k factorial. Multiple permutations can be derived from one combination. So what does this actually mean? Let me go back to the previous slide. Let us take, okay, this particular permutation. Okay, so in this permutation, there is one combination. Okay, so when I take, what was this sentence again? Let me go back here. Multiple permutations derived from one combination. Let's take this combination. There is one more permutation possible here, which is A3, A2. So that's what it means. Multiple permutations possible from one combination, but only one combination is available in a permutation. You go back to your permutation. Okay, so there is only one combination. So when I change the order of elements here, that is the same combination again. So this sentence says multiple permutations is possible from one combination, but only one combination is available in a permutation. Okay, there are many results on permutation and combination. So you all must be more familiar than myself with all those results in the proof process. So we will not go through all those results in the proof. I'm not here to explain all of them. Will not indulge in details of all of those, but wherever necessary, it will be used. The recursive formula for C and K is given like this. So all of you must be familiar with this also. C of n comma k or nck equal to n minus 1 ck minus 1 plus n minus 1 ck. Okay. Now where C of n comma 0, whenever we have a recursive formula, we have to say the beginning. C of n0 is equal to 1, C of nn is equal to 1. Okay, this is called as a Pascal's triangle. In the computation of binomial, these are also binomial called as binomial coefficients. Okay, so this Pascal's triangle is a set of numbers, and the numbers come from this particular formula. So the row 0, we simply list a 1, and in the row 1, I write two numbers which are 1C0 and 1C1. Both of them are 1. So that is what is present in row 1. In row 2, we will list all the numbers of 2C0, 2C1 and 2C2, which are here. Okay. Now, if you observe this number 2, this is nothing but the sum of these two numbers. What is available here is a 2C1. So according to this recursive formula, a 2C1 is same as 1C0. Okay, so remember this formula, 1C0 and 1C1. Okay, when I add these two numbers, I get a number here. When I go to the third row, the numbers in the third row should be 3C0, 3C1, 3C2, 3C3. Okay, so I don't have to use the original formula of factorials to find out this number. All I have to do is add these two numbers to get this number. Okay, sum of these two is equal to this number, sum of these two is equal to this number, and so on. When I go to row 4, I will list all the values of 4C0, 4C1, 4C2, 4C3, 4C4. Okay, the first element always start with a 1 in the triangle. Last element in every row of the triangle is also 1. The middle elements are computed from the previous row elements. Okay, I add these two, then that should be this number. This 4C1 is written as 3C0 plus 3C1. 4C2 is written as 3C1 plus 3C2, etc. Okay, so this is called as a Pascal's triangle. It is useful in finding binomial coefficients. Okay, here is an application of permutation and combination. Counting problems are common in many areas. Some common daily life problems I'm listing here. You have won a lottery, and suppose you are allowed to choose 2 items from a display of 6 items to take away. The number of ways you can do this is 6C2. Okay, so this, all of you must be familiar with this simple arithmetic. A teacher has to make 3 teams of 4 students to compete in a quiz program. Okay, suppose this is a task of a teacher to select 4 students from out of a class of 20 students. The number of able students means that there may be 50 students in the class, but the teacher has experience that the chosen 20 are likely to win the quiz competition. So she or he wants to choose 4 students out of this 20. Okay, this is possible. Okay, 4 students and make 3 teams of 4 students in each team. Okay, so this is not the simple problem of 20C2. You won't get the answer of 20C2 here. I mean, that won't make, that's not an answer for this particular problem. For instance, if the class size is 5 and 2 teams of 2 students are required. Now, how many ways can this be done? So the team members can be 1, 2, 3, 4 or 1, 2, 3, 5. This is one particular choice. This is another choice. This is one more choice. This is one more choice, etc. Okay, so in all these, if you observe, you see that 1 is now a member of one team. Okay, that it is also possible to pick students. Okay, so without student 1 in any of the teams, like this 2, 3, 4, 5, 2, 4, 3, 5, 2, 5, 3, 4. Okay, now the total number of teams possible is, okay, here I had 12 and here I had 3, so total number is equal to 50. So this doesn't become, so I cannot simply choose, okay, 4 members. After all, I want 4 members to make up 2 teams of 2 students. Okay, the answer is not simply C of 5, 5C4. Okay, you have to work it out in a different way. In fact, it is this particular number, 4 into C32, 3 into C22. Okay, so this is the final answer. So you find out the class size. I mean, the number of total number of students you want. So that is this number 4. Okay, C of 3, 2, and then 3, leave out 1 from the total number of students you have chosen. That is this 3, then multiplied by C22. So yes, for instance, if there are 6 members in the class, okay, the number of 2 teams with 2 students possible is worked out like this. Okay, so first I'll start with a 5 into C of 4, 2. Okay, just decrement 1, 1 from everything here. I'll start with this number. Okay, this finishes counting all teams which has 1 in it. When I exclude 1, I'll have the number of members also to be 5. Then we already found out the total number of 2 teams with 2 students is equal to this much. Add that to this. Okay, so when I count, it will be equal to 45 in number. Okay, here is one more application, the same application continued. Okay, same application, different problem. 3 persons enter a railway compartment with 9 vacant seats. Okay, the number of ways the 3 persons can be seated is the first person has 9 choices. Okay, 9 seats are available. So the first person can choose any of the 9 seats. So 9 multiplied by the second person. After the first person has taken a seat, there are 8 more vacant seats. Second person has 8 choices. The third person will have 7 choices. So the number of seating arrangements possible is P of 9, 3, which is also 9 into 8 into 7. Okay, now a circular, this is a permutation problem. In the previous slide, we discussed a combination problem. Circular permutation is when the items are arranged in a circular fashion like this. Okay, so they are arranged in a circular fashion. There is no distinction between 1, 2, 3, 4 or 2, 3, 4, 1 or 3, 4, 1, 2, 4, 1, 2, 3, all are one and the same arrangement. So now the number of possible arrangements of 4 elements in a circular permutation is n minus 1 factorial. If it is sequential, it is n factorial. Suppose you want to break open a computer file. This is another daily life problem. Okay, you want to break open a computer file of your friend, which is password protected. You also know that the length of the password is 8 characters and all are numerals. Okay, so you may ask, how do you know all this information? You work with your friend so very close every day. He keeps typing passwords in front of the system. So you see him, there are 8 stars that is displayed. So from that you can guess there are 8 characters in the password, and he only uses a numeral keys whenever he types a password. So you know they are all numerals. A good guess, the digits are that of the friend's birth date, which suppose you also know that to you. Okay, you know that what is the birth date of your friend is. The number of attempts is 8 minus k plus r factorial. Okay, what is this k? K is the sum of repetitions of the digits. Suppose a digit, 1 or 2 digits repeats. What is the sum of repetitions? That you take it out from this 8. Okay, plus R. R is the number of digits that are repeated. For instance, if 2 digits appear in these eight digits, if 2 digits appear 2, 3 times, then the number of distinct digits is 5. The 2 digits are repeating, and then they are repeating this many times. If you exclude all of them, the number of distinct digits will be 5. That can be calculated from this formula of 8 minus, okay, k. K is the sum of repetitions, 2 plus 3. Okay, then plus whatever the number of digits that repeated, 2 digits repeated, so plus 2. When I simplify this, I get the same number 5. Okay, so you find out the number of atoms from this formula, which is equal to 5 factorial. Okay, so now this decides whether it is worth trying all those combinations, so that, I mean, you know that for, excuse me, I didn't make it clear. You know that the friend's birth date is involved in the password, but then you don't know in what order the digits in the birth date is made use of by the friend in making up the password. So that is why you have some number of trials to be 5 factorial. Now, how many 3-digit numbers can be formed using the digits 1, 2, 3, 4, 5, 6? Okay, when no digit can be repeated, this is another example. When no digits are repeated, okay, then the first digit can be chosen in 6 ways. There are 6 available digits to me, 6 ways. And because the second digit cannot take whatever that is the first digit, I have 5 choices for the second digit, 4 choices for the third digit, which is 6p3. Okay, when the digits can be repeated, okay, even when 1, 1, 1, 2, 2, 2, 3, 3, 3 are all allowed in the 3-digit numbers, now the total number of numbers that can be formed out of these digits becomes 6 into 6 into 6. Okay, here is a second set of applications. Probability is defined as the ratio of number of outcomes favorable to the event to the total number of outcomes. This very simple definition of probability. Here is very simple example which illustrates how the probability is calculated. For instance, the probability of getting an even number in the roll of a die. Okay, you must all be familiar with a die. It's simply a cube with different numbers on different faces of the cube. There are 6 faces of the cube, and the different numbers that appear in the cube is 1 to 6. So out of 1 to 6, 2, 4, 6 are 3 even numbers. So the number of outcomes favorable to this event of getting an even number is 3, divided by the total number of outcomes. Anything is likely to come up when you roll a die. Okay, so total number of outcomes possible is any of the 6 numbers 1 to 6. So 6 choices are possible. So the probability is 3 divided by 6. Okay, and the probability of getting a two spade cards in one draw of 2 cards from a pack. Okay, so I want 2 spade cards in one draw of 2 cards. I pick 2 cards from a pack. The pack will have 52 cards. So the total number of outcomes possible is 52C2. I can get any 2 cards out of the 52. So total number of outcomes possible is 52C2. Okay, number of outcomes favorable is I'm interested in getting spade cards. So the probability of getting 2 spade cards is 13C2. Why this 13? Because there are 13 spade cards in the pack. So 13C2 is the number of outcomes favorable to the event divided by total number of outcomes. Okay, this is simple ratio. Probability is simple ratio. It's always between 0 and 1. The calculation of number of outcomes favorable to the event. So here is an example where I want a probability for which I need to calculate a combination. One combination for the numerator, another combination for the denominator. Okay, so we require permutation or combination values. Okay, so in this example, I require permutation or combination values. This is an example where I use a combination to solve the problem. In some cases, this, for instance, in this example, the simple calculation of permutation itself is a solution. Whereas in this case, a combination or a permutation is made use of to find out a solution to the problem. That's the difference between the 2 applications. This is explained in these 2 lines. Okay, some more examples of computation of probability are shown here. If 7 cards are drawn at random from a pack of 52 cards, probability that 3 are red and 4 are black is given by this. Okay, 3 are red, there are 26 red cards in the pack. 3 can be chosen out of the 26 in 26C3 ways. And then 4 should be black. So 26 black cards are there. 4 can be chosen out of 26 in 26C4 ways. So this many outcomes are now favorable to the event. Okay, now I'm picking 7 cards from 52. So the total number of outcomes possible is 52C7. Okay, so here also I make use of the combination and then I find out what is the answer to the problem. 6 boys and 6 girls are sitting in a row or to be seated in a row. Find the probability that all girls sit together. So when you want like this, then all girls can be counted as one entity and I have 6 boys. So total number of entities are 7 in number. So 7 factorial is a possible arrangement. Now why is this multiplication by 6 factorial? The reason is the 6 girls are together, but they can be seated among themselves in 6 factorial different ways. So the total number of possibility of keeping 6 girls together and then finding a seating arrangement of 6 girls and 6 boys is 7 factorial into 6 factorial divided by, this is the total number of outcomes possible. Okay, so I can sit 6 boys and 6 girls. The total number is 12. 12 factorial is a seating arrangement possible of 12 different students. Okay, now when all girls sit together and all boys sit together, so when I want an arrangement like this, then this is a probability. Okay, so how do I get this? So all girls sit together, all boys sit together. So all girls can sit together and they can be arranged in 6 factorial ways. All boys should sit together and they can be arranged in 6 factorial ways. Okay, so I get 6 factorial into 6 factorial. So I get a 6 factorial square. Why is this multiplied by a 2? Because girls can sit first and then followed by boys, or boys can sit first followed by girls. So we have 2 possible arrangements like that. So 2 into 6 factorial squared divided by 12 factorial. Okay, so this is an example where probability is calculated using permutations, and this is an example where probability is calculated using combinations. So examples 1 to 5 in the previous set of slides. I suppose you will all have slides with you at the end of the session. You can go through it in leisure. Examples 1 to 5 are where permutation or combination calculation is itself answer to the problem. Example 6 and 7 like this, or where permutation and combination is a means to find the final result. So we'll move on to the next application of permutation and combination. Many problems in operations research are combinatorial in nature. For instance, traveling salesman problem. So I'll let you know what the statement of the problem is. There is a salesperson whose job is to visit several cities, meet people and promote his product and return back to his home city when the job is done. Now the tour begins and ends in his home city. He starts from his city. If it is Mysore, he starts from Mysore, goes to different places. Okay, takes however many days he wants to, then come back to his city, namely Mysore. The tour touches a city just once. So if he goes to Bangalore, his job in Bangalore should be done. Then there is no point in going to Bangalore again and then meeting some more people. He stays back in Bangalore, meets whoever he wants to. He finishes his job in Bangalore, then go to the next city, maybe Chennai. So given the cost of traveling from a city I to city J, it is desired to minimize the cost of the tour. Everybody wants to do some optimization. If the company is spending money on him, the company will want to minimize the cost of the tour of the salesperson. A simple solution is to examine all possible routes. Remember, all possible routes means I have n factorial in number. He wants to visit n towns, excluding the hometown, of course. He wants to visit n towns, so there are n factorial for tours possible. And the associated cost. For each and every tour, you find out what are the costs and then find the minimum cost tour. Okay, so this takes too much of time. Even if it is 10 cities he wants to visit, a 10 factorial is a number of routes to explore. And when he wishes to, visit 10 cities, this is too big a number. 10 factorial is not a small number, and then you have to work out the cost of every tour, then find out the minimum. Even with a sophisticated program and a good computer, it will take too much of time. Nobody will want to spend so much of computer time to find out a simple answer like this. Okay, so unfortunately, there is no simple means of solving this problem. It recommended is a heuristic solution. Heuristic means an approximate but good enough solution. You can call it also as near optimal solution. Okay, so one simple heuristic is always move to the next nearest city. Okay, so this we also call it as a greedy procedure. You just find out what is closest next to you, just go to that particular town. Another heuristic is to work out an upper bound, the maximum you are willing to spend. Okay, so find out what the maximum you can spend on this whole tour itself, and then then systematically explore paths. Okay, so it's like 1 to 2 to 3 to 4 and back to 1. Now, suppose my upper bound in this particular example, suppose I have an upper bound of say 20. Okay, it should be possible to visit cities in a distance of 20. Suppose it is possible. Don't bother about this number. It is possible to visit them, make the entire tour with a cost of 20. Then what I do is I'll visit the city systematically in the order of 1 to 2, then 2 to 3. Then in that case, 1 to 2 is 12, 2 to 3 is 7, 19. Then 3 to 4 is going to cost me 4 more. So I will discard that particular path. So as soon as we exceed this upper bound of 20, you discard the partial path. So this way you will now discard, you will be able to reject so many partial paths, and then you will be left off with only few of the paths to explore until the end. Okay, now as soon as you hit a whole tour which is within your limit of upper bound, then you stop. You don't look for any other good. There may be better solution, but you are satisfied with that tour's cost itself. Okay, here is an example of a cost matrix for a 4-city problem. Okay, so you need not have you can imagine a graph, but then you need not have a graph at all. This is a matrix of cost. So these zeros represent the cost from going from city 1 to city 1. There is no cost involved, so they are all 0. This is going from 2 to 2, city 2 to city 2. That's also 0. Okay, so this number represents cost of traveling from city 1 to city 2, city 1 to 3, 1 to 4, etc. So if you look at the matrix, it is always symmetrical. There may also be some special cases where the cost of going from this way is less, whereas the cost of coming back from 3 to 1 is more. It's also possible to have a non-asymmetric matrix, but what I have shown here is a symmetric matrix. The same thing can also be formulated as a graph. You have a graph of 4 vertices. There are only 4 cities here. Okay, and then make an edge from 1 to 2. There is a way of reaching 2 directly from 1, and the cost is equal to 12. You put a number 12 there. So similarly, you can fill this, or the matrix entries can now be used as weights of the edges in this graph. Now, some tools of this simple 4-city problem is go from 1 to 3 to 2 to 4 to 1. Now, what are the costs involved? From 1 to 3, the cost is 15. So it is 15. And then from 3, I move on to 2, the cost is 7. So add a 7 to this tour. And then from 2, I go to the city 4. So 2 to 4 cost is 10, add a 10. And then from 4 to, I have finished all visits of cities 2 to 3 to 4. So go back to the starting city of 1, for which the cost is 4 to 1 is 8. So when I add all the numbers, the cost of the tour is 40. Now, one other tour possible is, so why not 1 to 4? If I go 1 to 4, I get an 8, and then from 4 to 3, 4 to 3, yes, 4 to 3 is here, which is 4. Okay, and then 3 to 2, 3 to 2, 3 to 2 is 7. When I add up, I get a 31. See, there is a difference in the cost between these two tools. So you have to work out what is the minimum cost. So for that, what is the number of possible tools of 3 with the starting city? We'll always assume the starting city to be 1, and then you come back to 1. Okay, number of possible tools is 3 factorial. So you will have to find out what are the 6 different costs involved, then chooses minimum cost tool. That is called as a brute force solution. Examine all possible paths and then select the minimum. So which we already discussed is not possible even for a 10 city tool. Exact solutions are solved. Okay, there is an exact solution possible for this traveling salesman problem, which is using dynamic programming. Okay, so this some of you may be familiar with dynamic programming. There are methods to eliminate bad parts. This is one such example. Okay, so work out a rough upper bound of the whole cost, whole tool itself, and then keep discarding the partial parts whenever you exceed this upper bound. Okay, so there are methods of eliminating bad parts and thus reducing the solution size. So one more example. It is also an operations research problem. A Chinese postman problem is something like this. That's also a graph problem. Imagine a graph with roads he visits as edges and the intersection of roads to be vertices in a graph. The postman has to traverse through all edges, okay, to deliver mails to the houses in the streets. In this traveling salesman problem, there is no necessity to traverse through all edges. For instance, a tour of 1, 3, 2, 4, 1. We don't visit this edge 1 to 2 and 3 to 4. Okay, in the Chinese postman problem, we need to traverse all edges. The edges are now roads and the houses are located on the roads, and the postman has to go through all the edges to deliver mails to the houses. The objective here is to minimize the distance traveled. Okay, and here the vertices may be revisited. So in the traveling salesman problem, you will visit the city exactly once. Here, the vertices can be revisited, but then minimize revisit of edges. Sometimes you have to visit edges again. So otherwise, let us go back to the same problem of the simple graph problem. Suppose these are the roads. Okay, now he wants to visit every road. That is possible only when he visits certain roads again. Okay, you traverse the road 1 to 3, then this road, then this road, then this road, then this road is left off, traverse that. Then one more road from 3 to 4 is left off. So how will I go from 3 to 4 unless I traverse this road once again? Okay, so it may be inevitable in some cases to revisit edges, but then we have to minimize such revisits. Only then the cost of the tool will become minimum. This is also a combinatorial problem. There are many ways of completing his tool. Exact solutions are available. Again, for this problem, there are exact solutions, but they are very tough. By tough, what I mean is it is very expensive. Maybe it is costly. Costly can also mean it is a lot of time-consuming problem. Okay, here is one more example of this is application set 3. In one more problem in set 3, optimal storage problem. The formulation is like this. There are n files with varying sizes to store in a computer. The computer has limited storage. Not all files can be stored. So I would like to store the maximum number of files in the computer. This appears to be combinatorial. Okay, so one possible solution is find all possible subsets of files. Okay, and then the corresponding sizes of each and every subset. Then find the one whose size, one means one particular subset, whose size means the subset size, okay, not the file sizes, the subset size is maximum. But the optimal solution can be easily found than this tedious method. So I don't have to go through this exercise of finding all possible subsets. Okay, somebody has taken pains and then shown that the optimal solution is very simple for this particular problem. What is the solution? The method is to store the files from the smallest to the biggest and stop when the storage cannot hold any more files. Here is a simple example. Now suppose the storage size is 15 and if the file sizes are 2, 4, 6, 8, 12. Okay. Now I have already listed the files in the order of the sizes, in increasing order of the sizes. Okay, now the method says that store the files from the smallest to the biggest. So store this. Okay, then 2 out of 15 is gone in the storage. Leftover storage is 13. Then store this. Then 6 out of 15 is gone. I'm left out with 9. That can hold this 6. Then how much of space is left out? 2 plus 4, 6 plus 6, 12. Okay, only 3 more is left out. That cannot hold this or this. So you stop. So how many files I have placed in the computer? I have placed the first 3 files. Okay, what is the total storage I have consumed? It is equal to 12. Okay, the sum of all these file sizes, which is equal to 12. Okay, this is the optimal solution itself. You can check that for this simple problem, there is no way of storing 3 files other than putting all these 3 together. Okay, if I can hold this one and this one is possible, I can store 12 and 2. That is file 5 and file 1. Okay, it is possible to store with this, but then it makes out to be, it is only 2 files. Okay, so my objective here is to store the maximum number of files. Okay, so for this itself is a simple procedure. Now let us take the same problem. Okay, there is a change in the objective. Still I have files and I have a limited storage in the computer. My objective is now changed. It is now the I want to use as much of storage in the computer. Now my number of files is not mattering anymore, but I want to consume as much storage in the computer as possible. Okay, it is to use the storage in the computer to maximum. Now it becomes a combinatorial problem. Okay, the only way is to find out all subsets of files and the associated storage sizes, and then find the one which utilizes the storage to maximum. So all these problems are typical combinatorial problems and have elegant solutions. Most of the problems I have told, not most, all the problems I have shown you have solutions, but the problem is they are very tough, except the previous problem of storing the maximum number of files. They have elegant solutions to reduce the work to minimum possible. Okay, and there are also so many heuristics available to reduce the work to minimum possible. Several heuristics available. Okay, now let's take the same example as before. I have a storage size of 15. I have 5 files to store, and I have these are the file sizes. Okay, now the objective here is to use the storage in the computer to maximum. So what is now the optimal solution? One solution is 12 plus 2 equal to 4. Okay, so I'm wasting only a space of 1 in the computer. And another way is 6 plus 8, 14. That also works out to be a wastage of just 1. So the solution is store files 1 and 5 or files 3 and 4, so that you do a minimum wastage in the computer. Okay, now we'll move on to the next set of applications. Okay, security of messages are ensured by encrypting messages. The previous set, that is application set 3, was about problems in operations research. Now we move on to the next application area. Okay, security of messages are ensured by encrypting messages using keys. Okay, keys will usually be a binary string and will be of fixed length. An attacker wants to break open a file. All he has to do is use all possible keys with a file and decrypt, and one of the keys will definitely open the file. This is called as a brute force attack. Okay, so I'm illustrating a brute force attack here, but my key is not a binary string. I'm using some other way of encryption. This is called as a cipher, Caesar encryption. Okay, now suppose the message has English alphabet characters. All of you know there are 26 characters. And let us assign numbers to these characters beginning from 0 and it ends with 25. Okay, here is now the various characters listed out to you, and then the numbers assigned to each and every character in a serial order. Okay, the encryption formula is y is equal to, this is the encrypted text, x is the original text. Okay, I add a 4 to this, okay, because everything is now a number, all characters converted to numbers, add one number 4 to that. This is called as a key. Okay, x plus 4, and then this may exceed 26. I cannot translate it to a character, so do modulo 26. So now this number will always be from 0 to 25. So that will now map to another character. Okay, for instance, the character E. E is now encoded as E's digit is now a 4. Okay, E is now encrypted as. Okay, what do I do for an encryption? Take this, convert it to a number, add a 4, do a modulo 26. 4 plus 4 is 8. 8 more 26 is 8 itself. 8 is now the character I. So instead of sending E, we send it as an I. Okay, so this you do it for each and every text, each and every character in the whole message. Now, suppose you want to send a message, run to your friend. Because suppose you both are mischievous. Now you want to escape, so you want to tell your friend to run. So you don't send it as this run, but then you encrypt it and send it to him. So how is the encryption done? You translate the characters in this message itself into numbers 17, 20, 13. Where did I get this from? From this set of, from this table itself. R is now number 17. U is the next character in my message, that is number 20. N is the last character in my message, that is number 30. Okay, these are the numbers corresponding to the characters in the message. Okay, now do the encryption to these numbers using this formula. So 17 plus 4 is 21. Okay, 20 plus 4 is 24, 13 plus 4 is 17. Find out the corresponding characters. 21 is V, 24 is Y, 17 is R. So send it as VYR. Okay, so when this message is sent like this, even if an opponent captures the message en route, so he won't make out what the meaning of the message is, because this is not a word in the English text, English dictionary. So this, you are now doing, the encryption is done like this to protect the messages. Now, what will the attacker do? He can pick up this, and then suppose he knows this is the way encryption formula, but what he doesn't know is this number 4. He can try all numbers. How many keys are possible? 0 to 25. So try out all the keys. This is called brute force attack. Try the key 0. Okay, so if I do 0 addition to any x, I'll get the same number. So VYR will become corresponding digits 21, 24, 27. Add a 0 to everything. It remains 21, 24, 27. Convert it to characters. It remains VYR. So this is the recovered message with this key of 0. So this doesn't work. Now try the key 1. Then I'll convert these digits to, with this formula, I'll convert, I'm sorry, in the decryption, I have to subtract numbers. Okay, in the encryption, I add the number 4, in the decryption, I'll subtract the number. So I'll subtract a 1 from this. So I'll get 21 minus 1, 20. 20 is now U. Okay, so the first character is decrypted as U. The second character is Y in the message. The corresponding number is 24. You subtract a 1, which is your assumed key. Okay, when I subtract a 1 from this, I get a 23. That will show you the character X. Then the last character in your message is R, which corresponds to the number 17. Subtract a 1 and get a 16. 16 points to character Q. So this is now the decrypted text of this encrypted text VYR using the key 1. Okay, this also is not any word in English, so you try another key, namely 2. Then I'll get this to be the decrypted text. You try one more. This is also not making any sense. Try one more key. Okay, I'll get another decrypted text. Try this key. I'll get a decryption to be run, which makes sense. If this is a word, now you know what exactly the message sent to the other person is. Okay, this is called as a brute force attack. Now, why I have shown 3 dots here is I cannot decide this is the actual message, because there may be another key. Okay, it is possible there is one more key which also gives out a word, a 3-letter word in English, a meaningful word in English. It could be that could be the message, or this could be the message. So we will not know for sure what the message is unless none of the numbers later, subsequent numbers from 5 to 25, none of them give you a meaningful English word. Then you will decide this is the X1 message. So the continuation of the same application set forth. In reality, keys are binary strings. So in the previous example, it was a very simple cipher, which is not used anymore by anybody. Okay, and it is very simple to attack. So in reality, keys are binary string of length 56 to 128 bits. Then a brute force attack will require 2 to the power of 56 keys. Okay, 56 bits means there are 56 places, and each place in the binary string can have 0 or 1 value, 2 possibilities. So thus I have 2 to the power of 56 keys possible. So this many keys are to be tried out. Okay, and after trying one key, what do I get? I get another binary message. That has to be translated to English. And then I find out whether it makes sense or not. So this is a really difficult job. It's not very easy to do a brute force attack. Okay, so having said that, I'm going to contradict my own statement in the next line here. But attacks have become so very sophisticated. There are softwares available to do the attacks, and they do it so very fast. Okay, and a real-time attack on this key size is still possible. That is why they went on to a key of size 128 bits. So another set of applications, application set 5. You all must be familiar with the human genome, which is as big as 6 billion nucleotides. The entire genome is of 6 billion nucleotides. Okay, which there are only 4 nucleotides, which is called as AC, represented by ACTG. They have some biological words. Okay, ACTG are the symbols. The number of genes. What is a gene? Gene is nothing but a sequence of ACTG. A sequence of ACTG, which is marked by a beginning of the gene and an ending of the gene. Okay, that sequence, a sequence of nucleotides is called as a gene, and they have discovered about 20 to 25,000 genes, and it's coming. So sometimes it also reduces. Somebody else proves it's not a gene, it is some other sequence. Other lower order organisms have less number of nucleotides. Okay, human genome is the biggest. Other lower order organisms have lesser number of nucleotides. Now, how do scientists discover evolution of species? They have to examine the changes in the genetic sequence of genetic sequence of a monkey and a human being, then find out how much similar they are. Okay, so how is it done? They have to use some combinations. Okay, this combination is available in humans, is available in monkey also. That combination of pig is available in rat, and so on and so forth. So here we have an application of combinations. Change itself is nothing but a combination of ACTG. Okay, so I have mentioned a word like observing the change in the sequence. What is a change? Change is nothing but another combination of ACTG in various locations. Okay, now apart from nucleotides, the 3 nucleotides at a time is called as an codon. So 3 nucleotides is called as a codon. For instance, ATG. Okay, when I combine ATG, that is called as a start codon. That indicates the beginning of a gene sequence. Okay, a particular gene, every gene has to begin from this codon ATG. Okay, 3 at a time will now make a codon. Okay, not all 3. Okay, how many 3s are possible? There are 4 symbols. So how many 3s are possible? 4 into 4 into 4. Okay, even you have to consider this codon of AAA, CCC, TTT, GGG. So when I count all of them as a codon, this many number of codons are possible. And out of 64 codons, they have made 20 amino acids. That is, not all codons will now make a meaning. There are some codons which they have identified that have a meaning, and they have given it a name called as an amino acid. Okay, not all codons can become amino acids. Out of the 64, some 20 amino acids are there. That doesn't mean 64 minus 20, how many are there? 44. 44 are useless codons. There are some multiple codons which will be called as the same amino acids. However, not all 64 codons are meaningful. Combination of amino acids. Okay, what are these? Combination of amino acids. Amino acids itself is 3 nucleotides, and a combination of amino acids are called proteins, which make our body function. Now, similarity of organisms are found by detecting fragments of similarity in codons. So instead of going to nucleotides, they have programs to do similarity of codons. So find out how many codons are similar across organisms like humans and chimpanzees. All these directly relate to combinations of codons and nucleotides. Okay, so all of them are problems of determining the combinations of codons and nucleotides. Common combinations of codons and nucleotides across organisms. Often a disease this is another application of, this is totally different. This is for finding similarity of organisms. This problem is totally different here. A disease is now characterized by finding expression levels in certain set of genes. I have told you earlier, there are 20 to 25,000 genes in human. So out of that, if you are considering a disease like colon cancer, okay, they may be the colon cancer patients may have differential expressions. They made some genes out of these 20 to 25,000, some 7,000 gene expressions are measured, and they may be highly expressed. Some of them may be lowly expressed as compared to normal person. Okay, so we always compare the expression levels of certain sets of genes with normal expression levels. You take a patient, you take a person who doesn't suffer from that disease of colon cancer, measure his expression levels of identified, say, 10,000 genes, and then measure the expression levels of the same 10,000 genes of the person who is suffering from colon cancer. Find out what exactly is the difference in the expression levels. Okay, this they often do. This has become a regular medical practice nowadays. Numerous gene expressions of the order of 10,000 genes are measured. Okay, so you don't go for random 10,000 genes out of this 20,000 genes. So there are scientific studies which indicate this 10,000 genes are important in colon cancer. So they pull out expression levels of those 10,000 genes. Now the problem here is certain groups of genes with differential expressions are to be, okay, this is problem number 1. Okay, this is easier to address. I find out this, from the patient 1 to the normal patient, compare the expression levels of all 10,000 genes. I identified which groups of genes are differentially expressed. Now, the second problem is like this. Persons with the disease, the same disease, we are talking about colon cancer. I have now 2 persons with the same intensity. Okay, they have the same stage of cancer, say stage 1 of cancer. The patient 1 and patient 2 have stage 1 of the same disease, namely colon cancer. They have the same intensity, but they may have different groups of genes with differential expressions. This is another problem. The number of combinations of genes to look into are simply beyond control. First of all, we have too many genes. And also I have another problem here, that different groups of genes have differential expressions. Okay, this is another problem. So I have too much of combinations to explore, but there are ways to reduce the number of genes across samples. Okay, so many ways are available in bioinformatics. So we'll not go into the details more than this, but this is only to highlight. Okay, the permutation and combination are really useful in the problem of finding similarity of organisms and in the problem of finding which genes are responsible for a particular disease. Now we move on to the next application, set 6, which is some problems in economics are inherently combinatorial, such as minimizing cost of transportation of items from warehouse to outlets. So in this simple example, I have 4 warehouses. They are called as supply nodes. So that's why I use the label of S1, S2, S3. And then I have retail nodes, demand nodes, which are D1, D2, D3. They are retails. Okay. Now I have produced things here, then I have to ship it to these retail outlets and sell it, finally sell it. This, whatever the number I have shown in the matrix, are unit cost of transportation of item, moving one item from this supply to this retail outlet. Okay. And to move one item from here to here, from this supply to this demand node, I have a cost of 5, etc. Okay, now here are the details of what is the supply available and what are the demands for these particular demand nodes. Okay, so there is a supply of 200 at this supply node, 100 at this supply node, 50 at this supply node, 150 here. There is a requirement of 300 at this demand node 1, requirement of 150 at the demand node 2, 50 at this demand node 3. Now, when I add all these numbers, I get the same number as total supply equal to total demand. This is a simple problem. There are complicated problems other than this. So this is just to show you the effect of, the application of combination in this particular problem of transportation. Now, what is the objective? How can I distribute 200 items to this? How can I distribute 200 items among these demand nodes? So this is one way of doing it. Move 150, okay, to this demand node 1. Move 50 to this demand node 3. So when I move 50 to the demand node 3, already this demand is met. I don't have to move anymore. Okay, so that's why I have shown a dash here. Okay, now how do I distribute this 100? Or how do I meet this 150? Let us talk about meeting this 150. Okay, so I have a requirement of 150 here. 150 is not met in this. This is not a solution. Okay. Something wrong here. Okay. Let me add 200, 100, 300 is available here. What is that? This number should be 150. Sorry, the number here should have been 150. Okay. So I can now meet this demand of 150 using this supply of 150. So I will move everything from this retail, from this warehouse to this particular retail outlet. So this number should have been 150. It's not a 50, correct it as 150. Okay. So this is one solution. And then this is taken care of. This supply is taken care of. Now I have 150 here. So move it like this. Okay, then I have now met the demand of all these demand nodes. Okay, and I have also taken into consideration the constraints available at the supply nodes. So the constraint available at the supply node is satisfied here. 150 plus 50 is 200. Constraint at the supply node 2 is 100. I have not exceeded the constraint. The availability at 3 is, at the supply node 3 is 50. I have not exceeded the constraint. Okay, so this is one problem. This is just one way of distributing the items. This will have some cost. What is the, how do I calculate the cost? It is 150 into 4, then 50 into 7, plus 100 into 3, plus 50 into 2, plus 150 into 7. That is of total cost. There is one more. There are so many ways of moving this many items to this many demand nodes. Okay, so you work out another combination and that will give you another cost. So combinatorial problem is to find out what is the minimum cost schedule. Okay, so there is, that is this finding total, so many different combinations is too much. Fortunately, It's not required to find out all combinations and then find out a solution to this problem. There are more elegant solutions, which is also optimal. We do it using the linear programming. Here is another application in economics. Here is the assignment problem. Okay, this is the problem of assigning jobs to skilled workers. Okay, and this is the cost of assignment. Okay, there are 4 jobs and 4 persons can complete the 4 jobs. 4 jobs means 4 different jobs. And these people, each one is now competent to do all these different jobs. And these are the charges they will charge in completion of the job. The person 1 will charge you 50 rupees to complete job 1. Person 1 will charge you 44 rupees to complete job 2, and so on and so forth. Okay. Now our problem here is I want to assign 1 job to a person. So I don't want to assign all jobs to this person, to only 1 person. Okay, or multiple jobs to 1 person. Okay, so I want to assign only 1 job to a person and then find out. Okay, this is one possible assignment. Assign to job 1 to person 4, job 2 to person 2, job 3 to 1, job 4 to 3. If I do that, what is the cost of assignment? 1 to 4 is now 40. Job 1 to 4, sorry, job 1 to person 4, 29. Job 2 to person 2, job 2 to person 2, 42. Okay, job 3 to person 1, job 3 to 1, 35, etc. This is one cost. There are multiple assignments possible. Why not job 1 to 1, 2 to 2, 3 to 3, 4 to 4? What will be the cost? 50 plus 42 plus 38 plus 39. Okay, so many assignments are possible. This is another combinatorial problem. Okay, fortunately, we don't have to examine all combinations, identify the minimum cost assignment. Okay, there are other ways to do it, which is also based on linear programming. So I can take some questions if any of you have in this first topic of permutation and combination. So let me see if some of you have flashed some questions. No video, ma'am. Somebody has said no video. I suppose they have resolved their problems. Okay, row minima method. What is that row minima method? Prabhu, here demand equal to, I don't have any questions for myself. So I suppose I can move on to audio not clear. I suppose they're all satisfied. Ma'am, you talk bilingual language. Okay. So when you start lecturing, you forgot, you tend to forget your native language. You'll go on to the, it is less, we can add dummy assignment. Yeah. Okay, so this is only to show you, I have not shown you any complications of this assignment problem. For instance, one complication is person 1 may not know to execute job 3. In that case, I'll have to put a dash there. So, but we cannot leave out any cell. We'll have to fill it out with a cost. So in that case, what do we do? So I have not addressed any complications in the way. I have only given you the basic problems. And this is just to tell you how combinatorics is helpful. Okay, Vogels is best. Okay, fine. I agree. So my objective is not solving transportation problem. My objective here is to tell you here is a problem which uses combinatorics. Okay, anything else for me? If it is less, we can add 1 person. Veera Raghavan says if it is less, we can add dummy assignment with the cost 100. Okay. So, okay. I suppose there is no serious question. Okay, so I will try and use Tamil hereafter. When so many of you have expressed that I should do bilingual lecture, I'll try to do that. Okay, I think I'm going to move on to the next topic of, okay, mathematical induction. So induction is useful.
Ma'am, Pradeep here, ma'am.
Okay, tell me.
Good morning, ma'am.
Good morning.
Ma'am, I'll just take 2 minutes, ma'am, actually.
Oh, yes, sure.
Yeah. So teachers, this is to give you a brief introduction about Lalita ma'am. So Lalita ma'am retired as a professor, and she also served as chairperson in Department of Science and Computer Science in University of Mysore Department. So many of you may not have come across the amount of research that's been happening in University of Mysore. Basically, there is always a culture of interdisciplinary research there actually. So where Department of Mathematics, Department of Computer Science, and other departments and biological related departments, everyone, they work together on various problems. So that's a wonderful culture that has come up in University of Mysore. And Lalita ma'am has been part of Department of Studies in Computer Science, where she has done a lot of research in data engineering, and especially on image processing and text processing, information processing kind of areas. And she has also explored a lot of avenues in cybersecurity. And then recently, Madam retired from University of Mysore, and she'll be part of eBox colleges as the mentor for Department of Cybersecurity. So all three departments, that is BTech in cybersecurity, the faculty and the department will be mentored by Madam. And unfortunately, due to this COVID situation, it's been some time that we couldn't meet. But Madam is going to completely drive this. And this session is something very special for all of you because ma'am is one of a special researcher, and being a woman, so she has been doing a lot of research work. She has published a huge number of papers. So if you just type in Google Lalita Rangarajan, University of Mysore, you will come across many research papers published in top journals. Okay, so International Association for PR, IAPR journals, and a lot of pattern recognition journals papers have been written by ma'am. Okay, and then you will see a big team of people in University of Mysore, big team of researchers, almost 3 to 4 generation researchers there. Everybody would have done a lot of work in data engineering, pattern recognition, artificial intelligence, machine learning. And ma'am, if I am not wrong, I think University of Mysore department should be the one which would have published maximum research papers in the area of pattern recognition and machine learning in India.
Yes, definitely.
Yes, ma'am. So that's the background of ma'am, that you would have realized through the depth in which she would have been dealing with cybersecurity. So hope all of you are enjoying. Make use of this session and work out all the exercises that has been designed by ma'am. Okay. So thanks a lot. Have a good day. Ma'am, thank you, ma'am.
Okay, thank you. Thank you for this nice words. Okay.
Thanks a lot.
Okay. Shall I continue with the lecture?
Yes, ma'am. You can continue, ma'am. Please.
Okay. Okay. Now, induction, we'll move on to the next topic of mathematical induction. Induction is useful to prove a set of statements which can be put in 1-1 correspondence with a set of natural numbers. Before the discovery of induction, proof methodology for a set of statements is as follows. That is, you know something to be true, and from that you find out a proof for S2, S2 implies S3, S3 implies S4, and so on, until you reach whatever Sn. Okay, that's how proof was being done. So since induction, it has become a very simple process. This method is fine for a finite and small set of statements. However, it is not possible for infinite number of statements. Now, here is the basis of induction. Given a statement over n, okay, inductive proof is done in 2 phases. Statement is shown to be true for certain n. Okay, the smallest n for which the statement is true, usually the smallest n for which the statement is true. Then the theorem is assumed for a certain k and shown to be true for the next k, namely k plus 1. This is the principle of induction. It is done in 2 steps. First, we show that the statement is true for a small n, smallest n. Then we assume it is true for a certain k of bigger than the smaller n, smallest n, and then prove that it is true for k plus 1. Okay. Then in these 2 steps, the theorem is proved. Here is a simple example. Now, suppose you want to show, now how do I mix Tamil? I'm very confused. N less than 2 to see so many English words come. I may as well finish up in English and then chat with you in Tamil finally. Okay, so show that if you want to show that n is less than 2 to the power of n. Okay, now this is what I want to prove. Now I first show that it is true for 0. Is it true? Yes, because this will be 0 is less than 2 to the power of 0 is 1, 0 is less than 1. So P of 0 is true. Now we assume P of k is true. That is, you assume k is less than 2 power k. Okay, and then I show that this particular relation is true for k plus 1 also. Okay, now how do I show that? I have made an assumption like this, add a 1 to both sides, still I have a less than in between. Okay, sorry, I should have written it as, here is another mistake. It should have been 2 power k plus 1. This plus 1 is not in the power, it is 2 power k plus 1. Okay, now here it is, the correct version is here. K plus 1 is less than 2 power k plus 1. Okay, now 2 power k plus 1. This 1 is less than 2 power k. So this 2 power k plus 1 is less than 2 power k plus 2 power k. And now when I simplify this, this becomes 2 into 2 power k, which becomes 2 power k plus 1. So finally, what I got is a k plus 1 less than 2 to the power of k plus 1. That is, the theorem is true for k plus 1 also. So I have shown 2 steps of induction, and that completes the induction, proof by induction. Okay, here is some 2 more examples. I think I need not go through them. You all must be very familiar with stuff like this. Let me skip that. The application 1 of induction 1 is like this. Okay, some definite, I'm going to pull out logic and the corresponding logic circuit in the computers. And therefore, I'm going to introduce you something called a well-formed formula as well as some logic gates. இது ரொம்ப சிம்பிளா தான் இருக்கும், ரொம்ப பயப்படுறதுக்கு ஒண்ணும் இல்ல. Okay, some definitions, algorithms are inductive. Some definitions, algorithms are also inductive. It need not be, induction need not necessarily be for proving propositions. It can also be for making definitions and designing algorithms. Okay, well-formed formulas. Okay, in short, we write it as WFF, well-formed formulas. In mathematical logic are defined inductively. Okay, logic is about truth values of propositions. Okay, so this is itself, this is called as a proposition. Okay, so the truth value of a proposition. Statements are, okay, denoted by, okay, propositions are also loosely called as statements. They are denoted by letters in English like this, P, Q, etc. Okay, so proposition P can be, it is raining. Proposition Q can be, it is not sunny. Anything can be called as a proposition. Now, operations on these statements are called logic operations. They are this many in number: and, or, not, implies, if and only if, or also called as biconditional. They are called connectives or operations. And their symbols: and is denoted by this symbol, or is denoted by this symbol, not is denoted by this, implies denoted by an arrow mark, biconditional denoted by this. Okay, now truth tables of compound statements indicate when the statement is true. Okay, truth tables of some connectives are shown here. So if I use an and, I have to now necessarily have 2 propositions. So it operates on 2 propositions, P and Q. So here is a truth table. So under what conditions of P and Q is this compound statement P and Q true is what is indicated in this table. Okay, when P is true, Q is true, P and Q should be true. When P is true, Q is false. When one of the statement is false, then compound statement is false. When P is false, Q is true, then it is false. And both are false, it is false. Okay, that is basically This and statement is true only when both the components are true. Otherwise, it stands to be false. Here is the truth table of disjunction. This is also called disjunction or OR operation. Okay, so this disjunction is true under these cases. That means when one of these compound statements, one of the propositions in the compound statement is true, the disjunction is true. When both are false, the disjunction is also false. Here is a truth table of NOT statement. Okay, NOT is an operator used with only one proposition, so I don't have another Q in this table. Okay, when P is true, not P is false. When P is false, not P is true. Okay, this is what implies. Okay. Now here is the inductive definition of well-formed formula. A statement variable, that is simple proposition P, Q, A, B, etc. are all well-formed formula. Okay, this is like a basis of induction. If P is a well-formed formula, then so is NOT of P. Okay, so with a NOT operation, if I use one simple NOT operation with any proposition, okay, I'll get this particular statement that is also agreed to be a well-formed formula. Now, if P and Q are well-formed formula, then so are P and Q, P are Q, P implies Q, P double implies Q. They are all well-formed formula. That is, if I use any valid logic operator and make out a compound statement, then resultant will again be a well-formed formula. Now, the last step in the inductive definition goes like this. A string of symbols with statements, operators, parentheses is well-formed formula. If and only if it can be obtained in finite applications of steps 1 and 3, 1, 2, 3. Okay, that is P and Q are R. Okay, A and B are C. Okay, that is derived out of applications of these three steps. That turns out to be a well-formed formula. So, for example, this is well-formed formula. I have only this I got is in the basis of induction only. Here is the definition of well-formed formula. Now I have used multiple steps of this. When this is well-formed formula and when this is agreed to be well-formed formula, then this also becomes a well-formed formula. Okay. Now this is well-formed formula. This is well-formed formula. So if I use an operator R according to step 3, this becomes well-formed formula. According to step 2, this becomes well-formed formula. Okay, so whenever a string of symbols, what does a symbol can contain? A simple proposition with logic operators and valid parentheses. Okay, so I can't put parentheses here alone. Okay, valid parentheses. That will create a well-formed formula. Okay. Here is the first application of induction. Okay, so that is a continuation of the same logic only. Statement logic defined so far is true value. That is, a compound statement can be true or false. It can't be anything in between or anything else other than true or false. A similar situation arises in various electrical and mechanical devices also. For instance, some devices which have two states or switch, a simple electrical switch which is on or off. Okay, a vacuum tube or transistor which is used in computers. Vacuum tubes are all outdated, but of course in earlier computers they are conductive, non-conductive. Okay, they can be in the state of conductive or non-conductive. A clutch, which is a mechanical device, it can be engaged or not engaged. So there are many devices which are bi-state, like your logic propositions, compound formulas. Two switches connected in series. When I connect two switches in series, okay, which is equivalent to an AND gate, I'll show you what the gates are. So don't be very skeptical about what this new thing coming up. Okay, two switches connected in series will allow current to pass through only if both are in on state or both are true. Okay, on is equivalent to true of our propositional logic. This is a status of the device, and this is the status of our propositional proposition. This is something equivalent to AND operation in logic. Okay, and AND operation in logic will translate to AND gate. two switches connected in parallel. If you connect a switch in parallel, when one of the switches is in on position, it will allow the current to pass through. Will allow current to pass through if one of the switches is on. On is equivalent to true state, of course. This is same as a concept of OR operation in logic. There are other gates in logic like NOT gate, NOR gate, XOR, XNOR, NAND gate, so many things. Every logic expression can be represented by a connection of logic gates in a specific way. Okay, if I have a complex logic expression such as this, I can find out a connection of logic gates. Now, whenever this statement happens to be true, that logic gate will now return a value of 1. That circuit of logic gates will return a value of 1. Okay. Now, every logic expression can be represented by a connection of logic gates. The component propositions or statements in logic are inputs to the connection of gates, and the output of the connection returns 1. Okay. Then the corresponding logic expression is understood to be true. And if the output of this connection returns 0, then the corresponding logic expression is will return a value of f. Okay, there is an association between what the logic circuit returns and what is the value of the logic expression itself is. So when I show you more slides, you may be able to understand better. Just wait with me for a few more minutes. Everything will become clear. Okay, so this is a figure of logic gates. You don't be bothered about this. Here is a simple AND gate. This is OR gate. This is symbol we use for AND gate. We'll take two symbols, X and Y. These are our propositions, and it will return an output. Okay, OR gate will also take two symbols. It will return an output. And what is the output? The output is given in the form of a logic table. Okay, this is your NOT gate that takes only one input, and what does it return? That whatever it returns is explained using a logic table or a truth table. Okay, these are all different gates. What exactly is the application I'm discussing about? Here is the application coming. A computer program is a set of instructions or statements. Instructions can be logic expressions. Some instructions can become logic expressions. And logic expressions are nothing but well-formed formulas. And well-formed formulas are defined using induction. Computer evaluates these expressions during execution of the program. For every logic expression, there is an equivalent connection of gates. When the output of the connection of gates is 1, the expression is understood to be true, and execution proceeds accordingly. When the output of the connection of gates is 0, then the expression is understood to be false, and the execution proceeds accordingly. Slide next shows why the decision making sometimes has to be done by computers at hardware level. Okay, so this is a borrowed slide from our website. I'll show you what it contains. So sometimes you don't have the software execution of these logic expressions. Okay, that is implemented. The gate circuit itself is implemented at a hardware level. Here is an example which shows what is the necessity of doing so. Okay, here is a simple computer. It does only the laser cutting, and nothing else is done by this computer. Okay, UV lasers at around 100 watts are very dangerous. They can start fires, and if you see the light from it with your naked eye, it can blind you in 0 time. And they also need to be, whenever you finish cutting, they need to be water cooled or they will burn up in seconds. So if you want to do the cutting, you have to be careful about so many things. You have to close the device, and otherwise, if it is open, you may lose your sight. And then you may have to have the water cooling system ready. Suppose there is a malfunction in the water cooling system, you should not allow the cutter to be operated. Okay, so these are some of the conditions. So the power to the laser needs to be shut off under a number of conditions. What are they? The first condition is, if the control computer has finished cutting the shape, we ask it to shut off. the laser should shut off. Okay, if the water cooling unit fails, then the laser power needs to shut off. And if some idiot opens the door, okay, if the device door opens in to the laser compartment, then the laser should not be operated, because there is a danger that somebody can get in contact with the laser beams. If the emergency stop button is pressed, then the laser needs to go off. These are some conditions. These are the 4 conditions under which you should always check these conditions, and then only the laser is now should be switched on. Computer, so the condition for the power supply to remain on is it is and of all these propositions. If the computer has finished, the computer needs it. Okay, when the computer needs to do the job, okay, only under that condition you can operate it. And when the cooler is working, as soon as cutting is over, it has to be cooled. So when the cooler is working, and when the door is not open, and when the stop button is not pressed. So this is nothing but is simply implemented using several AND gates. Okay, so this is a logic problem and needs some logic, and we need to calculate this not of this and of this and of this and of this. So all these things should be evaluated. So what are the gates used here? One NOT gate here, one AND gate here, and one AND gate here. Okay, the resulting signal goes to the laser. Okay, now you could argue that, so you may say that why is hardware implementation necessary? Because there are software malfunctions possible, or software is not often written properly. So you make sure that it functions proper. If you want to make sure this always functions properly, you make it hardwire it. Okay, and to make it foolproof, so you can also have another software which does the same function. So if both hardware decides the laser can be on, and if the software tells so, then the laser is now safe to be operated. Okay, this is a simple example to show how a sequence of conditions are tested. Conditional statements are simply propositions, and then you implement it using the and several kinds of gates. Okay, that completes the application 1 of induction. It states that the use of well-formed formula and the corresponding logic gates in the execution of some statements in the program. Okay, here is an application of induction, the second application. The sets can also be defined inductively. It's not necessary that proof induction is useful for proof process. Okay, sets can also be defined inductively. Here is an example. Okay, the first example says 3 belongs to P. If this is now a set, 3 belongs to P. If for xy belonging to P, x plus y will also belong to P. Okay, only those elements from steps 1 and 2 are in P. You may ask, when I start from just P, one element in P, where is the scope for finding out x plus y? Why not x is equal to y? With 3, I make 6 in the set of P. Okay, 3 plus 3 belongs to P. Then with 3 and 6, I get more and more elements in P. Okay, now finally, what is P? P is nothing but the set of all positive integers beginning from 3 and multiples of 3. Okay, here is another example of building a set using induction. Inductive definition of n minus 0, 1 goes like this. 2 belongs to P. Okay, we start with the 2. 0 and 1 are ruled out in the set. Okay, 2 belongs to P. 3 belongs to P. Then if x and y belong to P, then x plus y belongs to P. So only elements from steps 1 and 2 belong to P. Okay, so this is now, this set of statements will now give us a set n minus 0, 1. Now these definitions are useful when you have to code and generate the series. You may ask, what is the utility of, when I can simply say multiples of let x be the set of all elements, which is a multiple of 3. Why not do it that way instead of this inductive definition? But sometimes you may want to generate a series like that. For that, this inductive definition may be useful for programming. Okay, now computer programs, this is another application of induction. Computer programs are instruction sets. Okay, so a set of instructions make up a program. These contain strings of different forms, such as variables, constants, expressions, etc. One instruction can have variables, constants, expressions, operators, etc. Okay, now finite automata, context-free grammars are machine forms which can accept certain strings over an alphabet set, and these are used by compilers. Lexical analyzers are a part of compilers. They determine if a string is a valid identifier. Okay. They find out if there are rules for making a identifier. Okay. Each programming language will set its own rule. Two participants raised hand. Means, I don't know, should I respond to their question just now or can it wait?
At the end, ma'am.
Okay, fine.
Yes.
Lexical analyzers determine if a string is a valid identifier. There are rules for naming an identifier. Okay, some in early days, Fortran will allow only characters, a letter and a digit in naming an identifier, and it should always begin with a letter. And there are only 6 characters allowed in the names of an identifier. Compiler has to determine if the string is an identifier. Now, when it is doing the compilation, it has to pick out this identifier portion. I find out whether it is a valid identifier. Otherwise, will notify the user that it is not. There is a problem with the particular line, and this is what is the problem. Now, identifiers are nothing but regular expressions, and the machine equivalent form is a finite automata. Okay. So regular expressions are defined inductively. This is how induction comes into picture now. Okay, so regular expressions are defined inductively. Now here is the definition of regular expression. Sigma's regular expression is nothing but a set. It is a special set. That's all. Sigma is an alphabet set. The alphabet set is nothing but basic symbols over which strings are constructed. Okay, operations on sigma that are used to derive strings are plus, which denotes the union operation. This is a set operation. Concatenation. Concatenation, there is no symbol. We just write 2 strings together. That is called as a concatenation. And star, a closure operation. Okay, definition of regular expression goes like this. As I told you, it is inductive definition. Okay, sigma be an alphabet set, such as 0, 1. Okay, it can be as simple as 2 symbol set, namely 0, 1. Okay, first line of definition says empty set is a regular expression. Okay, this is an empty set, that is a regular expression. Okay, the set epsilon is nothing but null string. Okay, blank string, that is a regular expression. The third line says for each A in sigma, for each sigma in sigma, okay, set A is a regular expression. Okay. If R and S are regular expressions, then so are RS. RS means concatenation of regular expressions. R plus S means union of regular expressions. R star means closure or regular expressions. Okay. For example, here is an example. It may be clear when you look at the example. Let sigma be 0, 1. Now this 0 is now, this is a bold 0, means it is a set containing the element 0. That is a regular expression. Okay. See, simple A. If any symbol belongs to sigma, the set containing that symbol is a regular expression. So this 0 is nothing but the set of 0. That is a regular expression. 0 plus 1 is a union of set 0 and set 1, which is set 1, 0. Where is it? This one. This is a regular expression. Now, what is this set? Closure means this set. The closure always will include the null string epsilon and this 0, 1. Okay, in addition to that, any number of concatenations, 0, 1, appended with 0, 1, 0, 1. Okay, to this string, you add that string, concatenate that string. To this string, you concatenate this. To this, you concatenate that. Okay. Like that, any number, or why not to this string concatenate the same thing. So these are all the set string patterns that will belong to this set of 0, 1 star. Okay, so what is now the pattern? Pattern is 0 followed by 1. There are no two consecutive zeros in this set. There are no string in this set which has two consecutive ones. Okay, so this is how we find a particular pattern using a regular expression. Okay, now what is this after all? The 0 plus 1 star is always any string over 0, 1. Okay, that will generate any string over 0, 1. And this side is any string over 0, 1. In between is a 0, 0. So what this regular expression means is that set of all strings over 0, 1 such that it has a 0, 0, 1 somewhere. Okay, remember this 0 plus 1 star can also have 0, 0, but it need not have 0, 0 in it. So by putting a regular expression, by showing a regular expression like this, you make sure that the set represents all strings over 0, 1, which necessarily has 0, 0 somewhere in it. Okay, so this is about the definition of regular expression, which is an inductive definition. And regular expressions, or the machine form of regular expression, is a finite automata. Instructions can have many components, variables, constants, operators, etc. We already discussed that. Compilers will read instructions and translate these to machine languages. The instruction should follow rules of the language. Okay, validity of instructions. Okay, instruction means it can, if it is an assignment statement, the right hand side is an expression, the left hand side should be an identifier. Okay, so you cannot have expressions on the left hand side of an assignment statement. So validity of instructions can be checked by a context-free grammar, and the machine equivalent is a push-down automata, which will declare whether the sentence is acceptable or not. And the context-free grammar, language of context-free grammars are also defined inductively. Context-free grammar itself is defined using induction. Okay, so this is how induction comes in the compilers. Induction is useful to recognize an identifier, which is a subset of regular expression, and that regular expression form is a machine form is a finite automata. Okay, so this finishes. Okay, the last application of induction is here. Recursion and induction are closely related. Some definitions, expressions, functions, series. Okay, series is recursive, you all know. I'm going to discuss series and sequences shortly. Okay, we already discussed some definitions on induction. That is, well-formed formula is defined inductively. Regular expressions, context-free grammars, all of them are defined inductively. Okay, expressions can also be inductive. For example, a function like a factorial, okay, series, Fibonacci number series are all defined recursively. It is what is utility of recursion is it is easy to code a recursive formula. If you want to write a formula for finding, write a computer program to find out a factorial, okay, look at the inductive formula that gives you 2-line code for a factorial. If you want to code for a Fibonacci number series generation, look at the recursive formula. That will give you a code in 3-4 lines. Okay, this is the use of recursion in programming. And also that it is easy to prove that the program is correct when it is a recursive program. Okay, so a involved proof is not needed when it is a recursive implementation. Okay. Now, there finishes, here we have finished the second topic of induction. So if I'll go through this chat and then find out if any of you have a question for me. In that case, I will spend a couple of minutes addressing the questions. Okay, somebody has said from SZ, ma'am, there is any condition for choosing the values P, T, T, F. What does this question mean? I suppose it's not for me. Is there any condition for choosing the values? No, there is no condition. This is a question by SEZ. Okay, the user SEZ. Is there any condition for choosing the values TTFF for P and TF for Q in the logic table? No, there is no such condition. Only thing is you have to exhaust all possibilities of, so this one. So all possibilities of true and false values for P and Q. This is all is a total combination of true and false for P and Q. There is nothing else. I haven't left out true for both of them, true for first, false for the second, false for the first, true for the second, false for both. Okay, there is no condition for choosing like that. You can order it in any way you like. So when I change the first entry to be true false, then I have to remember I have to put a false in the first entry here also. Okay, it's differ to or not NAND gates for trustable. I don't understand the question. It's differ to and or. No idea. All possible. That I address. Nice explanation for well-formed formula. Okay, thank you. I don't understand the question by Prabhavati K. So if she can word it differently, I can try to follow what the question is and then tell her the answer for that. Maybe I'll wait for her to. Is Prabhavati there? So can you just type in what question is, phrase it differently so that I understand what the question is. It's differ to and or not NAND gates. Sir, trustable. No idea what the question means. Okay. So without wasting time, I'll move on to the next topic. Maybe in the end, if we have time, I'll clarify all questions. Okay. The next topic today is binomial theorem. Okay, so this theorem is about algebraic expansion of powers of two terms, okay, such as x plus y the whole to the power of 8. Okay, yeah, traditionally this 8, that is an integral number, but of course there are other versions where it can be non-integral also. Yes, x plus y power 8 equal to, you all know what this expansion is, 8ci x to the power of I, y to the power of 8 minus I. The binomial coefficients are symmetric. So when I evaluate what is 8c various i's beginning from 0 to 8, these are the values. 8c0, 8c1, 8c2, 8c3, 8c4. Then 8c5 is same as 8c3. 8c6 is same as 8c2. 8c7 is same as 8c1. Then 8c8 is same as 8c0. Okay, so the binomial coefficients are symmetric. They can be found from row 8 of Pascal's triangle of numbers. Remember in the first topic of permutation and combination, I showed you the Pascal's triangle. You can go to the row number 8 and then that will tell you what are the various binomial coefficients. An interesting variant of the theorem above is when one of these, in this binomial terms, when 1 reduces to 1, okay, 1 plus x power n. This is often used in various forms. It is nci x to the power of n minus I. There is no necessity to write 1 power I, it is always 1. So it is simply nci x power n minus I. You can also write it as nci x power I. Because the coefficients are symmetric, I can also write it as this. By the way, this theorem is proved using induction. Okay, now here is a figure, okay, that gives you an idea of what the binomial expansion is about. Here is a plus b power 1. Okay, so a is, this red portion is a, the blue portion is b. Okay, a plus b. So I have a red line and a blue line. They are of different lines. When I add them, it is as though I make a single line of these two. Okay. Now when I do a square, now you do a square of a dimension a by a. Okay, the same dimension you take and then complete a square, and then do a square of this dimension b. Okay, and then you always know that a plus b the whole squared is a squared plus 2ab plus b squared. And what you do with these two squares is now you take this square and match it with this, make the two corners coincide, and then complete the resulting square. Now whatever this area is equal to a plus b the whole squared. So what is this area? I have an a squared. Okay, this side is a, this side is a. This red is now of area a squared. This blue is of area b squared. This rectangle green is of area a into b. This side is b, this side is a. So this area is a into b. This area is a into b. So I have 2ab. Okay. So what I get finally is area of the bigger square. Now what are the sides? The sides are made up of a plus b. Okay, if it is a plus b the whole cube, you find out a cube of side a plus b, and then find out what is the volume of the cube. That will tell you what is the a plus b the whole cube is. Okay, and the various terms are also explained using various parts of this cube. Okay, so this is about the binomial, a simple illustration of binomial theorem. Okay, so how do you explain it using figure? Here is the application 1 of binomial theorem. Okay, so there are numerous scientists who worked on, beginning from Newton's days. He generalized the theorem to real powers of n. Instead of taking it to be an integral power, he used it for a real power. Okay, that is, it is a real number. It can be even negative or positive. Okay, a C of Rk is not usable anymore in that binomial expansion. So this, how do I find this? If this becomes a real number, I cannot find out this C of Ri, but instead there is another definition. Okay, so this is now found as R into R minus 1 into R minus 2 into R minus k divided by k factorial. Okay, this is also true if R is an integer. If R is not an integer, we use this definition of CRK. Expansion has infinite number of terms. Okay, this expansion x plus y the whole power r will have infinite number of terms. So whereas in the binomial theorem, when this is an integer number, you have finite number of terms, which is n plus 1. Here you have infinite number of terms. When r is non-negative integer, binomial coefficients are 0. Okay, so when r is a non-negative integer, so this is also usable for an integral value of power, namely r. Okay, so even when r is equal to integer, I can use this formula. So you may ask what happens with this infinity. But beyond certain r, when k becomes greater than r, okay, so when this summation, when I becomes, I should have written I here, when I becomes greater than r, you will see that the binomial coefficients are 0. Okay, so I don't have RCK when k is greater than r, so they all become 0. So we have only r plus 1 terms, and the expression is, and what the right hand side will simply become the original binomial theorem. The generalized binomial theorem leads to several interesting and important series. This discovery leads to several series, right from square root of 1 plus x. Okay, the geometric series when r is equal to minus 1. Okay, when r is equal to minus 1, when it is 1 minus x power minus 1, what happens? This geometric series. Okay, in general, when r is equal to minus s, where s is not an integer, what happens? For s is equal to half. Okay, so when s is equal to half, r is equal to minus half. So go back to this, you get this series. So all these series are possible. They are all interesting series and lot of applications are there. All of them are possible with this generalized binomial theorem. Okay. Now to continue the same application, okay, you all know that E is nothing but 1 plus 1 over n power n as n tends to infinity. Okay, so this is the definition of E. Now, how is binomial expansion. You can do a binomial expansion of this 1 plus 1 by n power n. Okay, when I do the binomial expansion, allow n to tend to infinity, I get this series for v. Okay, this is very useful in programming as implementations. So this is so many things in programming has to be a series. If you want a cos x, sin x, etc., are all given here, are all applications of binomial theorem. Okay, so all of them series are useful in implementation of evaluation of cos and sin and e power in using computers. Binomial series for special cases of 1 and a small x is useful tool in many sciences, especially physics. Okay, 1 plus x the whole power alpha is approximately equal to 1 plus alpha x. This is true under these conditions. Combination of de Moivre's formula and binomial expansion gives rise to two important series, namely cos nx and sin nx. Okay, Stirling's approximation for n factorial is possible because of binomial theorem. Okay, they are all somewhat involved proof. So I'm just doing an outline of showing you the end result. N factorial equal to this. This is very useful in finding the complexities of algorithms. This particular formula is useful in finding complexity of algorithms. For instance, the comparison sort algorithm. You sort a set of numbers using this algorithm. Namely, there are many ways of sorting numbers. This is one such algorithm. Comparison sort algorithm has worst case complexity of log n factorial to the base 2. Okay, I know this. And I have a very big n, such as 50. So 50 factorial. Who is going to find out what is 50 factorial? Then find out what is log 2 of 50 factorial. So that I need to know what is the maximum time I need to spend in sorting 50 numbers using this comparison sort. So instead, I'll use this Stirling's approximation. Okay, this is not tedious to compute, whereas 50 factorial is very big number. This is very difficult to compute. So find this and then use it here and then do log 2. That will give me what is the maximum time I need to do. I need to spend in using comparison sort on sorting of 50 numbers. Okay, so the Stirling's approximation is possible because of binomial theorem. Cos x sin x are possible because of binomial. Series expansion is possible because of binomial theorem. Worst case complexities of sorting algorithms reflect the maximum number of comparisons. Okay, this is already told. Okay, so finally, okay, if in a computer you want to find out what is calculators, computers, there is always a need to find out e squared, e cubed, e to the power of 1.3, etc. Where are we going to find out all of them by this series expansion? Where do we get the series from? From this binomial expansion. Okay, if we always ask for in the calculators cos of something, sine of something, where are they getting, where are the computers and calculators getting them from? From the series expansion. Where are they coming from? From binomial expansion and de Moivre's formula. Application 2 of binomial theorem. Binomial coefficients are used in computation of probabilities. We already discussed in length computation of probabilities of random variate that has binomial distribution. Okay, binomial distribution is founded upon the binomial expansion. An experiment that has binary outcomes. Okay, binary outcomes, two outcomes, we'll often call it as a success and failure, is called Bernoulli Trial. Okay, a simple experiment such as say tossing a coin. I get two outcomes. One outcome is a head, maybe you call it as a success. The second outcome is a tail, you call it as a failure. Okay, so that is called as a Bernoulli trial. Tossing a coin is Bernoulli trial. Now suppose I roll a die and then I want to find out whether the outcome is even or odd. That is also a Bernoulli trial. Okay, so a success, a number, appearance of numbers 2, 4, 6 are all called a success. When numbers 1, 3, 5 appears, you may call them as failure. Okay, so there is a probability associated with the success, and what will be the probability of failure? It will be 1 minus p. Remember, the sum of probabilities of all outcomes should always be 1. So if success probability is P, the other outcomes probability, namely failures probability, should be 1 minus P. The random variable X of number of successes out of n Bernoulli trials has a binomial distribution. Okay, and the probability of X is equal to R is given by this expression. Now, what is this? These terms are terms of the binomial expansion P plus 1 minus P the whole raised to n. Okay, so this is the probability of a random variable which has binomial distribution. What is binomial distribution? N Bernoulli trials collected together is binomial distribution, and you count the number of successes out of n trials. The probabilities are terms of binomial expansion. This is called this particular equation itself is called as a PMS, or probability mass function. Sorry, PMF, probability mass function. Application 2 of binomial theorem continues. Here is an example to say to tell you how binomial distribution is useful in computation of some interesting probabilities. Binomial distribution is useful when there are independent trials with two outcomes. Suppose that the factory manufactures integrated chips with 5% of manufactured chips to be defective. Then the probability that 10 out of 50 randomly selected chips are defective is given by, okay, 50C10, 5 by 100 the whole raised to 10, 95 by 100 whole raised to 40. So what is this? This is the probability that one chip is defective, or it is also called a success probability. Okay, don't get confused with success means it should be bad. It's not like that. Okay. So probability of a chip being defective is 5%, which is 5 by 100. So P is equal to 5 by 100. So probability that the chip is good is 1 minus P is 95 by 100. So we are now asking the question of the probability that 10 out of 50 is defective. So 10 out of 50 can be chosen in 50C10 into P to the power of R, 1 minus P to the power of n minus R, which comes from this particular formula. P of X is equal to 10 is equal to C of 50 C of 50 comma 10. P is now 5 by 100 whole raised to 10. 1 minus P power n minus R now becomes 100 minus 10. Oh, okay, out of 50, sorry. 150 minus 10. Suppose that, okay, here is another example, okay, so which is more relevant for today. Suppose that in a town of 2 million people, 10% are tested for COVID-19 and 2% of the tested people are positive. Suppose you attend a function where 100 guests were there, okay, so including the host. Suppose you mingled freely with all the guests, then probability of you getting infected with the virus can be found using binomial distribution. Okay, so 2% of this, whoever is tested turns out to be positive, so we'll extrapolate it and take it to be the rate of positive among the whole population. So 2 in 100 are affected or tested positive. Okay, and then the remaining 98 in 100, that is 1 minus P, or not, or negative. Okay, I want to know that what is the probability? Suppose you mingle freely with all the guests, probability of you getting infected with a virus. The assumption is that even if I talk to one person, if I come close to one person, I'll be infected. So the probability is calculated using binomial theorem like this. C of 100 comma 1 or 100 C1 multiplied by, okay, P to the power of R. R is now 1. Okay, 1 minus P to the power of n minus R. Okay, n minus R is 100 minus 1, that is n minus R. Okay, this is calculated like this. Now suppose you are very cautious and you come in contact, close contact to only 20 guests. Okay, so you Always keep distance, and then you come in contact, close contact with only 20 guests. Then the probability that you can catch the virus is 20 C1. Okay, instead of 100 C1, it is 20 C1, 2 by 100. This P remains the same thing. Okay, P raised to 1, Q raised to 19. Q is same as 1 minus P raised to 19. Probability that none out of the 20 you came in contact with has the virus, or probability that you are safe, is given by this. Okay, none out of means 0 is infected. Okay, so this is a ratio of infection, so that P is raised to 0, and the ratio of not infected raised to 20 minus 0. Okay. This is the probability that none out of the 20 you came in contact has the virus, or you can also call it this to be the probability that you are safe after attending the function. Now, negative binomial distribution is where you continue doing the trials until you see R successes. Okay, the TR be the random variable. Now, suppose TR is equal to N. Okay, that is, you continue to do the trial until you see N successes. To compute to see R successes, okay, you continue doing the trial until you see R successes. That random variable is denoted as TR. Now, suppose TR is equal to N. So what does that mean? That means that R minus 1 trials did not see the nth success. That's why I had to continue to R trials to see all the N successes. So that means R minus 1 successes happened in N minus 1 trials, and the nth trial happens to be a success. Okay, so that is what means by saying TR is equal to N. So this TR is equal to N, suppose that TR is equal to N is the event A, and B is the event that R minus 1 successes happened in N minus 1 trials. C is the event that nth trial is a success. Then A is nothing but B intersection C. Okay, both should happen so that TR is equal to N. Suppose this happens, that is, I had R minus 1 successes in N minus 1 trials, and then I drew an additional nth trial. I did not see a success. Then this TR is not equal to N. Okay, so this and this should happen, only then this can happen. So A is equal to B intersection C. So now P of A is equal to P of B into P of C. So this is now a formula in probability theory. I see you have a session to go through in future days on probability. That time all these things will be discussed, I suppose. That is, P of A is equal to, P of A is same as this, P of TR is equal to N, equal to P of B. P of B, where do I get P of B from? R minus 1 success in N minus 1 trials, I can find out using binomial distribution, this particular formula. P of C. P of C is getting a success in one trial, which is P. Okay, so this is called as the PMF of, or the probability mass function of negative binomial distribution. Now here is the use of negative binomial distribution. Go back to the previous COVID example. Now you suppose that you keep meeting people hoping that they are not infected, or you calculate, oh, so and so is very cautious about movements, so she would have been careful, and so it is safe for me to come in contact with them. So you keep meeting people, hoping that they are not infected. Suppose that you are well read, and then you have a trusted information source which says that spread of the virus is possible only when you come in close contact in a limited time to more or 5 or more infected people. So that is what it means is, if you come in contact with 4 people in 20-30 minutes time, you are likely to be not infected. So suppose you have a trusted information like that. Okay, now I'm interested in calculating the probability that I'm safe after coming back from the meeting, and I have met 20 people. Then I can calculate it using this negative binomial distribution, okay, which is nothing but P of TR is equal to 20. I'm meeting 20 people. So likelihood of meeting, okay, are people within the, are infected people within this 20 people, right? And R can be 1 to 4. That is, I may meet 1 infected person or 4 infected person, up to 4 infected person. Beyond that, I'm not safe. So the probability that you are safe can be calculated using negative binomial distribution. So under this particular scenario of trusted information, if you have this information, and with this information, if you want to work out the probability, negative binomial distribution is the right distribution to use. I think I'll postpone the questions for the end, because otherwise we'll run short of time. Okay, so the last topic of today is sequences and series. Okay, the last topic is this. Sequences are a list of numbers. All of you know it can be numbers, it need not be numbers, it can be items or objects. Order is important in the sequence. Shuffle in the list means 2 different sequences. List can be finite or infinite. Okay, then the sequences can be infinite or finite. Generally, the sequences are expressed using a generating formula, such as this. A of n, the nth term of the sequence, equal to n squared minus 1. A of n is equal to 2 into A of n minus 1 plus 6. This is Fibonacci sequence. Okay, these two are examples of recursive sequences. This is a sequence which is where terms are expressed in terms of indices. Whereas here the nth term is expressed in terms of the previous term, so you call it as a recursive sequence. Now, in absence of formula, by looking at a list of first few members of the sequence, you will be able to find the subsequent terms and also find the generating formula. For example, if the sequence is 4, 7, 10, 13. Okay, so who cannot say that the next term is 16? Anybody can do that. Okay, now what is a recursive formula? It is 3n plus 1. Sorry, not a recursive formula, generating formula is 3n plus 1. Sequences are a list of numbers or objects. We already told that. Typically, sequence itself is a function whose domain is the set of positive integers. See, sequence itself can be considered as a function. Domain is a positive integer. Okay, the function is n squared minus 1. Series is a sum of all terms of a sequence. This says the differences between sequences and series. And in a sequence, numbers can repeat. For example, in the Fibonacci series, at least one term repeats, namely 1 that repeats. But in a series, there is no repetition. Some common sequences and series are where the next term is arithmetic series, geometric series, harmonic series are very common ones. Okay, where next term is the previous term plus a difference. This is how typical arithmetic numbers in the arithmetic progression is generated. Geometric progression numbers are generated typically like this: previous term multiplied by a ratio. Harmonic series terms are generated using or reciprocals of arithmetic sequence. Okay, here is an example where sequences need not be numbers. Suppose you consider outputs of 3 tosses of a coin. Okay, we have a list like this. This is also a sequence, but it is not numerical sequence. Sequences, there are many more. First, we'll focus on sequences, and then I'll list out some applications, then move on to series. There are many more types of sequences: Cauchy sequence, disjunctive sequence, interleave sequence. They are all special types. Okay, so many of you must be familiar with Cauchy sequence at least. Interleave sequences where you have 2 sequences and the odd terms come from one sequence number 1, even terms of the new sequence come from sequence 2. They are called interleave sequences. Cutting sequence, okay, this random and Recursive sequence is what I'm going to focus today. I'll list some applications of these 2 sequences. Random sequences are where the numbers in the sequence are random. Okay, now you can use a device to generate random numbers, but if you want limitless random numbers, device is not useful. You have to go for a formula for generating random numbers, such as congruential formula. This is called linear congruential formula. Okay, so you may have a question, what is the fun in using a formula and then calling it as a random number? I specify at least one x of 0, I specify a, b, m. Then if I specify everything, then I know what's exactly the sequence of numbers I get. Then why do we call it as a random? We don't call it exactly as a random, we call it as a pseudo-random number. That means they are apparently random. Now we have several tests. There are so many tests available to make sure that the sequence appears like a random sequence. They are not really random, but they have all the properties of random numbers. Then what is our problem? We may as well use a formula to generate random numbers because it's very convenient. This requires a, b, x of 0. It can generate random numbers in the range 0 to m-1. Numbers generated this way are called pseudo-random numbers. Here is an example. Suppose a, I tell you to be a 5, b is equal to 3, the seed to be equal to 4, m is equal to 7. Now what will be the random sequence? The first x1 is generated as a into x0 plus b modulo m. Okay, I have already told you what are a, b, x0 are. A is 5 into x0 is 4, 20 plus 3, 23 modulo 7 will give you 4. Okay, 23 modulo 7, 23, yeah. No, sorry. 5 into 4, 20. 20 plus 3, 23. 23 modulo 7 is 2. Sorry, I should have started with it. Okay. The first number itself is 4. And then I have a 2. With the 2, now what is the next number generated? 2 multiplied by 5, 10 plus 3, 13. 13 modulo 7 is 6. Then the next number in the sequence, 6 multiplied by 5, 30 plus 3, 33 modulo 7. 33 modulo 7 is 33 modulo 7. I forgot where I left. 33, 7 is 5. Yeah. Plus 4, 38. 28 plus 5 is 33. Yeah, 33 modulo 7 is 5. Then is 0, then 3, 4, etc. Okay. So there is no etc. That is all the numbers I get in the sequence. Remember, how many digits maximum I'll get? I'll get the reminders as 0 to 6, nothing more than that. So I got a 4, 2, 6, 5, 0, 3. Then I got a 4. Then what will be the next number? The same sequence again. Okay. So once you repeat a number in the previous set, then I don't generate any more new numbers. So now in this sequence, what is left over? I have got 1, 2, 3, 4, 5, 6 distinct reminders out of 6 reminders. Out of 7 reminders. So reminders are from 0 to 6, 7 in number. Out of that, I have got 6 distinct reminders. And what is left out? 1. That is left out in the sequence. I will never be able to generate 1 using this formula and these particular sets of AB. Yeah. Okay. So this is a good generator. In fact, you will not be this lucky always. You are likely to generate only half the set of reminders. So whatever choices you made of ABM is not bad at all. I have got 6 out of 7 reminders. Okay, random numbers are generated like this using a formula, and there are many tests available for randomness. When the sequence of numbers passes all these randomness tests, you don't have to worry. They will definitely be qualified to be called as a random set. Okay. Lot of algorithm systems require random numbers. So here are some examples. Okay, the first example I will take from computer security. Cryptography is a science where messages are encrypted. I already gave you a small example of cryptography elsewhere in permutation and combination, okay, which was a Caesar cipher. So where messages are changed, you essentially change it to some other set of characters and send it across. The purpose is even if somebody picks up the message en route, they will not be able to find out what exactly the message is. One-time security code you get in phones are nothing but random numbers. Often you do any bank transaction, you will get one security number, a security code, high security code. If only if you enter this, you can do transactions. So they are nothing but random numbers. When two people exchange secret messages, okay, they use a key. Okay, that key, they may use a key just for one-time sharing of messages. So that often happens. Okay, one-time sharing of messages, they use a unique key. So for that, that is nothing but a random number. Before sharing messages, they do some kind of handshaking procedures. They exchange some messages before actually sharing the secret message. That is called as a handshaking procedure. There are so many procedures available. So those things require a lot of random numbers. So usually the handshaking procedure is guided by a third party, which is called as an authentication center. Now here is a simple example of a handshaking method. So suppose A and B are two participants, they want to exchange a secret message. Now the C may be the authentication center. So A will now flash a message to C. Okay, this is message 1. It is like this. So always messages are encrypted. Whenever it is sent, it is encrypted. I am not telling you what the key is. Okay, the key of encryption between these two parties is going to be a secret key shared between A and C. Okay, a message is sent using the key shared by only these two people. Okay, now what exactly the message is? A says, reveals his identity. Okay, sends a random number, and then he will say that I want to talk to B. Okay, that is the message. It is encrypted. Now C, the authentication center, will respond like this. Authentication center will send a secret key. Okay, that is denoted by this KS, as well as F of N1. Remember, this is encrypted. Okay, using the key shared by these two people. So even if it is caught hold of en route from C to A, so it is unlikely that the secret key is exposed. One in 10,000 chances that this gets exposed. Okay, so this is still safe. And this F of N1, this F is again a function that is usually kept between an understanding of handshaking procedure between A and C. Okay, so they return F of N1. F of N1 can be a random number sent to +1 random number into some X, etc. Anything can become an F. Okay, so the A can verify when this message is received. A has received the session key. Okay, as well as he has received an F of N1. So he will check. He knows what the original random number sent is. He knows what F is. Now he will calculate F on this number. He will find out what this received F of N1 is, make a match of these two. If they match, then he will know that nobody else has tampered with this message. So that means this KS is safe to use. Now, at the same time, meanwhile, when he sends when this transaction 2 happens, C also sends the same key to B. Okay, so the same key is sent with a random number. And B again does a similar message. He reveals his identity, and also he sends a random number, a function of the random number to that. Then a verification takes place at C. Okay, then he knows that, okay, B is correctly responding. The message is coming from B only because of this usage of this G, etc., etc. Okay, so all these are typical protocols to make sure they are responding to the correct people. So you don't know what happens remotely. So C may be thinking he's responding to A, but he may be talking to somebody else. So to make sure that transaction happens between the genuine parties, all these messages happen this way. Okay, then finally, after this is all part of handshaking procedure, then again, it happens between handshaking between A and B happens also. So now the encryption of N3, another random number. Okay, now the encryption is done with this session key, which both of them have, A and B have here. Okay, encryption is done with this session key, encryption of a random number. Then the random number comes back as a function. It is again encrypted with KS. Okay, then after all verification, they come to know that A and B come to know that they are talking to each other, and then the key is not exposed, this key is not exposed, then the actual message transaction happens with the encryption of, encrypted using this key. Okay, this is all. How many random numbers are used here? 1, 2, and 3 random numbers are used here. Okay, so this is just one example of transaction between two parties. In real life, you are talking about so many pairs of people wanting to share secret messages, and there will be so many authentication centers. All of them require random numbers. Where are they coming from? From one or the other algorithm. In cryptography algorithms, random numbers are generated using seed and system time. They use a seed, and then they use a formula, and in addition to that, a system time. Okay, so in other words, so you or some handshaking procedures also include a timestamp here. So you also send a timestamp, and when it comes back, it should be within a small interval of time. And this message comes back from C to A, it should be within a small interval of time. If it is beyond a certain interval, then this is rejected. Okay, Kerberos is an authentication service package mainly used for dialogue or transaction with servers. There will be a separate server called as an authentication server, the purpose of which is to authenticate users who want to talk to a server. Okay, the authentication servers will generate what is known as tickets. These servers, tickets are nothing but some random numbers. These servers will recognize genuine users and provide tickets, which has also a time validity to users to communicate with the servers that renders the service. You often have a session key when you do a transaction with a bank, and then session key, if you use it delayed, you won't be able to communicate with the bank server. It has to be used within a certain time. Okay, simulation is another area where random numbers are extensively used. Simulation is nothing but the process of digital imitation of real systems. So here is an example where there is, which says there is a necessity to do simulation. A program written to analyze the traffic congestion at a junction. Okay, instead of actually executing a particular pattern of traffic signals in a junction, experimenting it, and then seeing so many accidents, you can execute a program to analyze the traffic congestion. So objective is to find out the optimal timings of the signal in the 4 lanes so that the wait time of vehicles to pass through is under limit. These inputs are, what are the inputs to this program, simulation program? The inputs are the traffic density, namely A, B, C, D, which are some parameters, traffic density of vehicles per minute. Okay, the density can be as simple as 3 in a minute in one lane, lane 1, 5 in a minute in lane 2, 1 in a minute in lane 3. Okay, or it can also be a distribution. Why not like this? Okay, the traffic intensity of lane 1 is exponential with parameter 4 per minute. Okay, it can also be a statistical distribution. Now, outputs are some statistics such as the average wait time of vehicles in each lane, an average of 0 vehicle time slots in each lane. Okay, so that means there may be a lane which is entirely empty. So in that case, you can reduce the traffic signal time of that particular lane. So this is also a useful measure of output, average of 0 vehicle time slots in each and every lane. So when you do it in a program, then you can change the various settings of this. So this is not changeable. This is not at your disposal. This is fixed. Whereas what you can change is the signal timings. You change the signal timings and then measure these 2 outputs. See if it is satisfactory to you. If not, you adjust the signal timings. Keep doing it until you have some satisfactory result of the output. Okay, so when you do this experiment using a computer and a simulation program, So you are not disturbing the existing traffic and not creating chaos on the roads. The general approach is observe the traffic pattern. I think this is the same thing. Okay. Observe the traffic patterns for some days and find the pattern of arrival of vehicles. These will be the inputs. Program will internally keep track of each vehicle and the arrival time, departure time, calculates the output. Okay, so everything done internally by the program. I'm running short of time, I guess. So many are raising hands. Maybe they all indicate that I'm going out of time limit. Recommend sequence is defined like this. Do I have time for this? Yeah, I have. Oh, okay. I think.
Yes, ma'am. You can take your time.
Okay, fine. Thank you. Recommend sequence is defined like this. A of n is equal to 0. If n is equal to 0, A of n is equal to n minus 1 minus n if this is greater than 0, if this condition happens. Otherwise, it is this. Okay, it is an inductive definition again. Also, and you can also say it as an induction. The sequences, the first few terms of the sequence goes like this. You can verify. The sequence look like an audio notes. When plotted, it looks like audio notes. So you have some ups here, 0, 1, 3, 6, then some down, then some up. Okay, then down, then up, then down, etc. It looks like audio sequence. Okay, so here are the values in the sequence are plotted. It looks like an audio sequence. Okay, this sequence is used in the steganography. It's again a security application. Is used in steganography of hiding two-dimensional images. Steganography is nothing but the art of hiding information, usually of one media, like audio hidden into image, text hidden in image, etc. Usually one media is hidden in another media and sent across. The contents of the image, the advantage of steganography is you are just sending a text hidden in an image. So you send an image to your friend and then an enemy captures it. He looks at an image. He won't know what is hidden in this. I mean, he will think that it is just they are sharing some images. There is nothing secret in it. But this doesn't send this. Whereas if you send the text as in some other set of jumbled characters, this raises curiosity of the attackers. Suppose I send steganography as A, N, G, R, H, Y, S, T, etc. Some other arrangement of letters. Then some attacker captures it and he thinks that, oh, something secret hidden in this. Why don't I arrange it in all possible ways, find out what the message is. Okay. Whereas in steganography, you just send an image. The image is not very much disturbed. So it looks like a plain image. Okay, but then there is a secret message hidden. The attacker is not interested in it. He doesn't want to do any de-attacking on it, but at the same time, there is an embedded secret image, a message. Okay, the contents of the image is arranged as a linear list. Here is an example how this recommend sequence is used. Contents of the image is arranged as a linear list from top left position to bottom right position. The values are chosen from this list in the positions of the recommend sequence and can be converted to audio signals. Okay, so you collect the signals, the pixel values at the positions corresponding to the recommend sequence, arrange it, and make an audio file of these and send it across. Thus, you are converting a two-dimensional image into an audio sequence and sending it across. So this is an example of steganography. Okay, I'm going to skip this. I have already exceeded time by a lot. Okay, one example of series. Okay, a simple example is when you have an investment, when you have investment of ₹1,000 with 4% interest per year and compounded annually, the net return is nothing but the sum of returns at the end of each year. Okay, this is an example of a series of finite number of terms. Series such as cosine, sine, log, e power x are useful in the design of computers. We have already discussed. So you have often requirement to compute a cos x, sin x, log x, e to the power of x, and these are computed as series. Almost all languages have these as library functions. Whenever these are to be computed, the sum of the successive terms are added one at a time. And then this addition keeps happening until two successive sums differ by a very small quantity. For example, you know, cos x is this particular series. If some user asks you to find cos of 120 degrees, then this series is computed like this. First, cos of 120 is taken to be 1. Then 1 minus this. One more term is added to that. Then the difference between this and this is found. Okay, if this is very small, then the successive terms are negligible. You stop. Take cos x to be this value. If the difference is significant, add one more term. Okay, now this will be taken as a value of cos x. Now compute the difference between this and the previous term. If the difference is small, stop. Okay, if the difference is large enough, you add one more term to that, etc. Okay, I think the rest of it is not okay. Fourier series is an important, has a lot of applications, particularly in image processing. And okay, JPEG is actually uses the this is the full form of this is discrete cosine transform, which is a form of Fourier transform. It is special case of Fourier transform. Okay, so that is what is the standard. This JPEG is now an image compression standard that uses DCT. Audio signals are mostly waveform. Anything that is in waveform, an approximation, Fourier approximation of that is very easy. The advantage of Fourier transformation is that it compresses well, and it is also almost reversible. You can get back the original signals almost, not exactly, but almost reversible. And also it allows you to compress it by a lot, and therefore you do this transformation you do the Fourier transformation on these waveform signals. So with this, I think this is the last slide. Yeah. So I conclude my session, and if I have time, I don't know, I think somebody should tell me what are important questions. Okay, thank you, ma'am. Very useful session. I think they all left already. I don't know. Maybe they all left in between. Okay, anyway. So this is all I wanted to talk to you about, the applications of the 4 topics given to me. Thank you so much for your patient listening. I hope this comes to use to some of you at least. Thank you so much for the organizers also.
Yeah, thank you, ma'am.
Thank you.
If there is time, you can just take up 1 or 2 doubts, ma'am.
Oh, yeah, sure.
Yeah.
Okay. So I browsed through this chat. It's
Okay, ma'am.
morning to you all. Okay. Google's is best. Okay. I addressed all these things. Somebody has suggested that Vogel's approximation is better for transportation. I agree with that. The purpose is not to suggest solution for the chosen problem, but to tell you that it is an application of computation, combinatorics. Okay. And it is used in game theory. Could you give examples on application of permutation in countable infinite sets? Okay, I think I don't have a slide for that. Okay, but there are applications. If you leave an email, I have the organizers have my email. If somebody is interested on more questions, I can take questions on my email and then reply you offline.
Yes, ma'am. Sure, ma'am. We'll just take the questions and share it across to you, ma'am.
Okay.
Thank you.
Yeah, that's better, because I think many of them have left.
Yes, ma'am.
Because I have exceeded the time. They must have got bored of the never-ending lecture.
No, ma'am. Almost 1,500 are there, ma'am. Zoom and
Okay.
YouTube together.
Okay.
Okay. Thank you, ma'am.
Yeah, thank you.
Thank
So
you, ma'am, for your.
can, share my email to them, and if
Yes,
anybody
ma'am.
wants any question, I can respond by email.
Yes, ma'am. Sure, ma'am.
Okay. Okay. Thank you.
Thank you, ma'am, for your detailed and lucid lecture on permutations, combinations, induction, recursion, binomial theorem, sequences, and series. All the applications that were cited during the lecture were very relevant and easily understandable. And the highlight of this lecture were your examples on COVID. And it's no secret that science and gender inequality are not on the best terms even in today's world. And even in modern days, women are very much underrepresented in fields pertaining to science and technology. And for centuries, women have been struggling for recognition of their academic achievements and research contributions. One instance for this would be that the Nobel Prize for Economics in the year 2019 was awarded to 3 people: an Indian origin Abhijit Banerjee, Esther Duflo, and Michael Kremer. But most Indian newspapers reported it as the Nobel Prize was awarded to an Indian origin Abhinit Banerjee and his wife. So this is the kind of recognition that women scientists are getting even in today's world. But born in a generation before us, you have established yourself as an eminent researcher, and you're certainly a good role model for all women teachers over here on how to be an excellent teacher as well as an eminent researcher. Thanks for your time, ma'am. It was a wonderful session.
Thank you.
And thanks to ma'am for sharing her lecture content with the eBox practice team 4 to 5 days in advance. So with the help of that lecture content, we were able to model many interesting exercises based on the examples that ma'am was citing in her lecture today. So you will have an enjoyable practice session today as well. So you should thank ma'am for that as well. Thank you, ma'am.
Thank you so much. So how do I have to do any logout or anything?
You can just click on leave, ma'am. There will be leave in the right top corner. You can just click on that.
Okay. Okay.
So, and for the teachers, the practice sessions will be enabled by 12 today. You can start working on the practice sessions from 12. Okay, thank you, one and all.